Okay, in this video, I'm going to continue talking about functions, and I'm going to specifically talk about compositions, inverses, vertical line test, and horizontal line test. So we know that a function is a machine that you give it input numbers and it outputs other numbers, the same or different numbers. Okay, and we've already seen how there's the mathematical notation to express such machines, such as the x squared function or the function that doubles a number. Okay, now you can combine two machines and you could use them at the same time, just like people use a washer and then they use a dryer. You can suppose you wanted to do two operations, so you can stack them in a sense, something like this. Okay, and that's called composition. The word is not as important as the concept. The concept is you first wash your clothes, then you dry them. So you apply one, then you apply the other. Now, what is the order? You apply the inner function first, and then the outer function. So, for example, if I had f of g of 3, okay, the first thing I ask myself is, what is g of 3? And that is 2 times 3, or 6. And now I can replace the inner function with 6. And then I ask myself, what is f of 6? Okay, so hopefully that's a reminder of what composition is. And let's do another example, and I'll ask you to calculate some values. Let's say the m function is equal to 2x plus 1, and let's say the n function, n as in Nancy, is equal to 1/3 x minus 4. Would you please calculate m of n of 0? Would you calculate n of m of 1 and m of m of 2 and n of minus 1? So there's no reason, if you start stacking functions, there's no reason you can't embed the same function inside itself. Okay, so try these. Let's see if you can pull these off. Okay, so I'm going to do the inner functions before I wrap it up. So n of 0, let's first get that. That's minus 4. M of 1 is 3. M of 2 is 5. N of minus 1 is minus 1/3 minus 1/4. That's minus 13/3. Okay, yeah, that's right. Now I can do the outer part. So for the first one, I'm going to do m of minus 4. For the second one, I'm going to do n of 3. And for the third one, m of 5. And then for the last one, m of minus 13/3. So let's do that. So m of minus 4 gives minus 7 for the first one. Then n of 3 gives 1 minus 3. M of 5 gives 11. And then n of minus 13/3. That one is going to be a little tricky. We'll have to work it out. 1/3 minus 13/3 minus 4. So minus 13/9 minus 4. 36 minus 49/9. Okay, if I believe I did that correct. So there you have it. There's composition. It's just you using a washer and then a dryer. Or for the last two examples, maybe you use the washer twice because there was a really dirty jacket you had to clean. And then for the n of n, maybe you use the dryer twice because something just wouldn't dry. That's the idea there. Okay. Now let's state the obvious, and then I'm going to state what the impact for graphs. Okay. If you input a certain number into a function, you should always get the same output. Okay. F of, like here I calculated n of 0 and I got minus 4, right? You shouldn't be able to come back on Tuesday and get -4, but then on Thursday you get +4, and then Friday you get 200. All right, that would be disaster. So you always have to get the same answer for the same output for the same input. Okay, that much is obvious. Now, when you graph a function, that means that certain graphs, it's not possible for certain graphs to be the graph of a function. Okay, think about what I just said. Every input has to have an output. Okay, can a graph be a circle? Okay, now suppose we were sitting over here. Let's say this was x equal to 1. Okay, what would the value of, let's say this is the graph of potentially of some function. Would the value of f be the point above x equal 1, or would it be the point below? You see, you'd have no way of knowing. So that's why you can't have something that's circular shaped be the graph of a function. Okay, let's do another example. What about if I had a graph that looked like the letter C? Okay, and let's pick a point here. This time let's pick one on the other side, -1. Okay, you'd have the same problem. Do you pick the height above or the height below? Okay, you can keep drawing all kinds of pictures of graphs that could not be the graphs of functions, and what they will all have in common is there'll be 2 points that have different heights on top of a certain x value. Okay, one way to see if a graph disqualifies itself is simply seeing if there's 2 points, there's 2 heights associated with any one x value. Okay, the way that people usually describe what we've just been talking about is called the vertical line test. Okay, imagine you drew a bunch of vertical lines on the graph, and if there's any place at all where you can touch the graph in more than one place, then it fails the vertical line test. Okay, so all of the red lines that I've drawn touch the graph in 2 places. Okay, so you might think, well, wait, doesn't that happen to every graph? Okay, well, hold on. We all know that a quadratic is a valid function, and you might know that the quadratic has the graph of a parabola. Okay, notice that if you start drawing vertical lines, notice that no vertical line ever touches the parabola in more than one point. See that? So there's nothing wrong with a parabola. Okay, so that's called the vertical line test. And on the homework, you'll be able to distinguish. There'll be some graphs, and you can use a vertical line test to see if a graph can belong to a function or not. Okay, let's now talk about inverses. So we've described functions, we've described compositions, the vertical line test. What about think about what it would mean to undo a function. Okay, here's a function that adds 1. All right, so f of 4 would give 5, f of 10 would give 11, etc., etc. What if I wanted to back up? Okay, I wanted to undo that. So suppose I had another function that instead of adding 1, it did the opposite. It subtracted 1. Okay, so f of 4 gave 5, but g of 5 would give 4. F of 10 gave 11, but g of 11 gave 10. All right, so can you see that I end up where I started at? Okay, if you had a function a that doubled something, then the inverse, let's call it the function b, would be a function that chopped it in half, because that would be the opposite. Okay, now one way to know if a function is truly, if a second function is the inverse, and now we're going to get to use the composition. So there was a reason that we were learning composition along with inverses. So If you take the composition of a function and its inverse, okay, f of g of x, so g of x is x minus 1, so this is the same as f of x minus 1. Well, that's x minus 1 plus 1, which is x. Okay, that is the test. When you take the composition of a function and its inverse, you'll always end up back where you started with an x. Okay, let's see if this works for the a and b. A of b of x. That means a of 1/2 x. That means double 1/2 x. That also gives x. It also works in the other direction. Go ahead and try, let's do it on the left here, g of f of x. See what that gives you. G of x plus 1, which is x plus 1 minus 1. And then let's try b of a of x. Okay, that's b of 2x, so we're going to half of 2x. Okay, so it works in any direction. Okay, either direction you get x. So that's the definition of an inverse. Okay, now one way you could solve for an inverse, let's do that. Sometimes it's not so obvious if you have more complicated functions. Like, what about if we had m of x is equal to 2x minus 1 divided by 3? Okay, so the opposite of multiplying by 2 is chopping it in half. The opposite of subtracting 1 is adding 1. The opposite of dividing by 3 is multiplying by 3. But what order do we do it all? That's kind of confusing. Okay, here's how you can solve for that. Write the function with y's and x's. Then swap the x and y. Like that. See how I reverse wherever there was an x I put a y, and wherever there was a y I put an x. Okay, so you swap the x and y. Now solve for y. So to solve for y, I cross multiply, and let's subtract 2y from both sides. So no, I'm sorry, I can't subtract 2y from 3x. Never mind, I was going too fast. So we have 3x equals 2y minus 1. So let's add 1 to both sides. So that gives 2y equals 3x plus 1. And then let's chop both sides in half. So 2y is equal to 3x plus 1 over 2. And that's the cleanest way to keep your sanity and find the inverse function. Okay, so maybe we'll call it, how about if we call it I for inverse? So I of x is equal to 3x plus 1 over 2. All right, and you can take the composition and convince yourself that indeed the composition will give you x. All right. Now, not every function is invertible. Okay, it might seem that it's no big deal to solve for the inverse, but here's the problem. Remember how a function's graph had to pass the vertical line test? Well, if you not every when you make what you want to be the inverse, you'll have issues with the inverse actually being a valid function for the entire domain. Okay, let me explain that. Let me take a different tack. Okay, it'll turn out that if you graph a function and its inverse, okay, let's say that, so I'm trying to explain what I just said now in a different way. Let's say you had a function that, like, let's say you had this purple line, okay, it's going to turn out that the inverse is going to be the same thing you would get if you reflected that graph over the line y equal x. So if I flip that purple line over that orange line, I would get let's see, I would get this green one. Let's see if I can get this right. Something like that. Okay, maybe green's not the best color. Let's go with black. Okay, so you see how the purple and black are the reflections along that orange line, and I meant that orange line to be y equal to x. Okay? Now, imagine flipping various graphs over the orange line y equal x. You'll notice that not all of them will pass the vertical line test. Okay? For example, let's put a big fat parabola on our graph here. Okay, so that's a valid function. Now let's flip the parabola over the orange y equal x line, and let's draw what we get. Okay, so if you reflect the parabola over that line, you will get this sideways parabola. Okay, right? Clearly, the black parabola doesn't follow the vertical line test. Okay, so then you ask, how do I know if a function is invertible? Okay. Well, what you do if a function is not, or if you want to know if it's invertible, the graph will, there's a horizontal line test. Okay, the problem with what you want to avoid is having functions that have horizontal pieces. Okay, the parabola right here on the orange parabola, this region right there had a flat portion, and it's that flat portion when you flip it over the yellow axis, it becomes vertical, and it's that vertical that we don't like. Okay, think about that. That's why there can't be vertical pieces. So we call it the horizontal line test. You draw a bunch of horizontal lines, and if they can touch the graph in more than one place, then it's not invertible. Okay, so to summarize, a graph can be the graph of a function if it passes the vertical line test. Okay, a graph can be the graph of an invertible function. Not only will it be a function, but an invertible function if it passes the horizontal line test. Okay, and of course it has to pass the vertical as well, because it has to be a function to begin with. All right, and a function that passes the horizontal line test is always either growing, so it's always moving up and to the right, or it's always decreasing, it's moving down and to the left. There's a fancy name for an invertible function that's called a one-to-one function. Okay, you don't need to necessarily get too hung up on the name, but the one reason it's called one-to-one, the best way to think about it is go back to the tabular method of thinking about functions. Okay, if we have a table, then there will only be, and let's say we listed a couple of values of functions. Okay, you will never have two x values that have the same y value. Okay, let me repeat that. You'll never have two x values that have the same y value. So for every y value, you have one x value. So that's why we call it one-to-one. Get it? So that's the tabular way, the tabular analog of the horizontal line test. Okay. Well, what do we do if a function is not invertible? Does that mean we just throw up our hands? Well, there is a consolation prize. Okay. You can have part of the graph be invertible. Okay, for example, the parabola was not invertible because when you flipped it over when you reflected it over the y equal x, that was the issue. Okay, however, what if we did this? Watch this. Suppose that instead of working with the entire parabola, what if I just work with half of it? Okay, so now I just have this I just have this half of the parabola. Let me draw it so that it passes the vertical line test. Okay, now let's reflect the purple, just that half of the parabola. Well, if I reflect that, so there's a graph of the inverse, and does it pass the vertical line test? Sure. Okay, every part of the purple and blue can touches all these vertical lines only touch the purple and blue graphs in one place. Okay, we knew that was going to happen we knew that this is going to be, the purple was invertible because it passes the horizontal line test. Okay, so you draw horizontal lines and they only touch the purple in one place as well. Okay, why does that work? If you want to know a trick, it's what I said. The graph is always increasing or decreasing. It's 1 to 1. Okay, that's what it looks like if it's 1 to 1. So what I just showed you, let's end with this. Functions that are not invertible may be invertible for restricted domains. So we only, if we just focus on just a small piece of the domain, a restricted piece, then we might be able to make a restricted inverse. Okay?